Hello everyone, welcome to this live stream. My first attempt at doing a live stream, so glad to have a reason to attempt this. Just gonna give ourselves a few minutes, make sure that this is actually working. If we can get a couple of hands up in the WhatsApp group, to know that people are seeing this, and to give the last few people a chance to get live, that will be awesome. Cool. I'm going to try to go really slowly through everything, so that there's enough time for questions to be relayed. I think we'll see how this goes, actually. A little nervous here. We're going to be going through the map reading Scoutcraft badge first up today. We'll be doing over 2 parts. So this first video is going to be the everything to do with compasses and bearings and all those things. And the second part we'll do the map side of things, scales, contours, and symbols, height planning, everything else that goes with that. So give me a few moments here while I get things in. My cat may be joining us as a guest host partway through. Right. So, let's see, we seem to have a couple of hands up going there, so people seem to be joining in. Right. Just so everyone knows, it seems there's about a 30-second delay between anything I say and what will actually appear on your side. So, questions will take a little bit of time to relay to me. Because of that, I am going to deliberately try and go quite slowly, and there will be plenty of awkward pauses, which is just me vamping to give time for questions to filter through. Cool. So, our first things first, I think, is going to be that, as I said, we're going to be dealing mostly with compasses in this first part, how they work, how we use them, and what north actually means, which is mostly what we use a compass for. So the first thing I think that we need to do is understand what one of these guys actually does. Now, it'd be quite easy to say that it just points to north, but it doesn't actually magically know how to do that. There's a bit of science behind it. I'm not going to go into all the technical stuff, but it's important to understand what this is actually doing. And ultimately, the little needle that we have inside here is a magnet. And what that means is it points to, well, it aligns itself along a magnetic field. Now, where is there a magnetic field, you ask? Hopefully we're not just thinking the one stuck to our fridge, but thankfully we happen to live on a really big magnet. That is ultimately what the Earth is. Now, I'm going to be using this as my stand-in Earth for today. And the first thing we need to understand about the Earth is, let's pretend that the little knot here is the North Pole. The Earth obviously spins, right? Let's draw an equator on here so that we can see our Earth spinning. Things I should have prepared earlier. is a very straight line I've managed to draw. Right, but here's our Earth spinning. Now, the Earth doesn't just spin. Let me try and get both myself and the Earth in the view at once. The Earth doesn't just spin upright. The Earth actually spins at a bit of a tilt. And that's going to come into play a bit. The fact that the Earth's got a tilt is what allows us to have seasons. That combination with the fact that it's going around the sun. But the Earth, obviously on the outside, is all rocky or wet in the case of the ocean. But underneath that, we go through a series of layers. And sitting at the middle of the Earth is a iron ball, effectively. Great big lump of iron, which is spinning. And it's actually spinning at a different speed to the rest of the Earth. All the various layers have their own speeds. If you've ever watched the very, very bad sci-fi movie The Core, a bunch of people try to travel down to the center of the Earth to restart it. That might give you an idea. But with that metal ball spinning in the middle of the Earth, that creates an effect that's called a dynamo. Actually, let's use this. Another stand-in Earth. This is a weird Rubik's Cube toy of mine. And what you might see in... can you see this on the thing? There's actually a series of spheres inside this, which are all spinning. In this particular example, they spin on weird axes. But in the Earth, they at least all spin on roughly the same axis. And what the spinning ball in the middle does is it creates what's called a dynamo. Something that we'll touch on if you get to high school physics or university physics. But a dynamo is effectively is metal spinning in a magnetic field, or an electric field rather, and that creates magnetism. That's how you create electromagnets, amongst other things. Anyway, this spinning ball of metal creates a magnetic field throughout the Earth. And thankfully for us, the magnetic field of the Earth lines up pretty much perfectly with the Earth's rotation. So that we wind up with a north magnetic pole and a south magnetic pole, which roughly align to our actual magnetic pole, or actual poles of the Earth. North and south are just words given to those two things. Right. So we've got this magnetic field, but the important thing to understand is that it doesn't perfectly align with the axis of the Earth. So although our true North Pole is here, right now our magnetic North Pole is somewhere off to the side. And it actually moves. The magnetic North Pole moves around a bit as the Earth's core spins. We've got a solid inner core, but then there's a molten core around that, which is actually a bit lumpy, and it's got lumps of metal floating around in it. And as those shift around, and as the rest of the Earth spins, and we get bombarded by solar winds and all sorts of other things that can affect it, the magnetic field of the Earth kind of wobbles around a bit. And what that means is that the magnetic field is constantly shifting. The magnetic North Pole is currently shifting. I think it's currently somewhere in Canada. The magnetic South Pole is actually quite far off the South Pole. It's a good part of the way to Tasmania. And the fact is that although we're going to have an actual axis that runs like this, our magnetic axis runs like this. And that's what our compass is going to be aligning itself to. The important question then is, how do we use that? Well, our compasses are going to point us towards magnetic north. Magnetic north, as I said, is slightly off-center, and it does move around. So anytime you're using bearings, and we'll touch on that a bit later, it's important to understand what the magnetic declination is. So what is magnetic declination? Well, let's have a look at our Earth. I'm hoping this is all visible. Let's pretend that our magnetic North Pole is a bit further away from our real North Pole. Now, if we're over here somewhere, I hope this is all going to be visible. True north is going to be from us pointing straight towards the actual true North Pole. But our compass is going to be pointing to a different place, and that is magnetic north. Now, in this particular example, they're quite far apart, and in this case, magnetic north is east of true north. But that's going to differ depending where I am on the Earth. If I'm, let's say, all the way down here, somewhere in this, then true north is going to be over there. But magnetic north is going to be a much thinner angle, but this time off to the west. So it's always important to check if you're working compasses and maps, and and it's important for you to understand the difference between true and magnetic north. To know where you are, what magnetic declination is at the moment, where you are. Let's see if I can pull up a cool website here. Give me a second. Let's pull this up. And there's these days it's quite easy to find out. There are websites that will give you the information quite readily. Let me find one here for us. And let's hop on over to my display. There we go. This website is literally just called magneticdeclination.com, and you can find out wherever you are. And here, pretty much in Delta Park, we can see that magnetic declination is 19.3 degrees west. If I play around a bit and we zoom out and find ourselves somewhere completely different, let's try Australia to start with. You'll find out here that their declination there is actually 6 degrees east. So you can understand that between 19 degrees the one way and 6 degrees the other way is quite a significant difference between where north actually might be. Let me pull myself back up. Right. So, as I said, it's very important to understand that. There's also something called magnetic inclination. That's somewhat less important to know about, but it can be useful. And magnetic inclination is how the magnetic field actually flows around the edge of the Earth, and how close to the edge of the Earth it hugs. That's the very what's the word I'm looking for? Naive way to look at it. The idea is that in my compass here, obviously it won't work when I'm holding it up to the camera, but the needle sits relatively flat in my compass because this compass is actually designed to work here in South Africa. I've had this issue before, when I was once gifted a compass that was actually designed for Canada. Now, the important thing to understand with our magnetic North Pole is that the point that it's pointing at isn't necessarily exactly on the surface at the North Pole. Depending on how things work, it can actually be slightly above the middle of the air or underground. But the magnetic inclination is what angle it is from you to the North Pole. And what can happen with that is that the compass that I had that was designed for Canada was effectively always stuck at an angle like this, because it was trying to point to something. It had been set up and designed to point to something that it was like trying to point straight through the Earth to get to. And that was a problem, because it meant that the needle actually kept getting stuck on the edge of the base plate. So instead of spinning nicely, it would get stuck, and even when I turned myself, it would just stay pointing in the direction it was. And so to use the compass properly, I had to hold the compass at a bit of an angle. Needless to say, it wasn't very useful. Provided that you've bought the compass in an area where you're actually going to be using it, it should be fine. They used to sell compasses in sort of world regions, that this one would work here and this one would work there. I think these days they managed to figure out how to make them so that they basically work as either northern or southern hemisphere compasses. But it's still something just to watch out for. Cool. I think that's most of the things we need to worry about with how compasses. Oh no, right. Obviously, as said, this is pointing towards the really, really, really big magnet that we live on. But the problem is, if you might say, well, how can any other magnet ever compare to the Earth's magnet? The Earth's magnetic field is actually quite far away. So although it's prevalent, it's not right here. So the question then becomes, well, what happens if there might be a weaker magnet, or something that's metallic that can also has magnetic properties, comes near this? Well, then the fact that it's nearby stops, overrides the fact that it's not as powerful as the Earth itself. So there's plenty of things you need to watch out for when you're using your magnet, using your compass. A good example would be metal objects, and you can watch here what happens as I bring this pair of pliers near to my compass. The needle keeps moving around to point to my pliers. How's this a problem? Well, you might have seen in a movie, someone's lost and they get out their car and they take the map out and they put it on the bonnet of the car and they slap their compass on the car bonnet. You've just put your compass next to a really, really big metal object. That's definitely not going to work. But you need to watch out for other environmental things that can get in the way as well. Richard on the WhatsApp group will probably chuckle right now when I talk about power lines, or possibly non-existent power lines. But if you're walking underneath power lines, again, you've got electricity and metal that combines to make a magnetic field. So if you're standing underneath a power line, you can't be sure that your magnet's going to be pointing in the right direction, because there's all sorts of interference. Something to watch out for, especially up here in the high veld, if you're hiking, is that there's actually a lot of iron in the ground, and you can sometimes sit down on a nice rock that actually has a really high iron content, and that can also cause problems with your compass. There's even simpler things. Sometimes if you're doing a mapping survey, which we'll touch in tomorrow's videos, mapping badge, if you've got a metal clipboard, that can mess around with you. There's plenty of ways that it can go wrong. Another important thing just to note is when storing your compass, try not to store your compass either next to anything else that's magnetic or metallic. Especially don't go and put it in a metal set of drawers, as that can have long-term impacts on the compass needle itself. Right, I think that's most of the things that we need to cover in terms of what magnetic or how compasses work. So let's now start talking a little bit about some different kinds of compasses. So it's popped up an image on the screen there now. But this type of compass that I've been talking about here, I'm showing you. You can see really neatly my name and troop written on there in my mom's handwriting. I've had this compass for a couple of years now. This is a base plate compass, or an orienteering compass, or a mapping compass. There are different names that get thrown around for it. And what this is particularly useful for is for when you're using your compass in conjunction with a map. That's why it's almost always transparent, so that you can still see the map through it. And we'll talk about a few of its features shortly and how those can help interact with the map. The way this one works is actually got a needle in the middle, and the needle is what points to north. And in this particular case, it's usually got a red needle. The red needle will usually be what points to north. Some of them will have a luminous side to the needle, or some other means of indicating which direction is north. It's quite important to know which one's north, else you can end up pointing yourself south. It's what's called a parallel error. You end up think you're following the right directions, you're just going completely in the wrong direction. So always important to know which direction of the needle is pointing north. Usually it's the red one. What you'll notice in this picture and on this one is that it's usually got some rulers down the side. Those will usually be denoted in various scales. We'll touch on scales in the next session, but that helps you be able to measure items on your map that you're working with. The question then is, how do we actually use one of these? Now, the method I generally recommend is the first step is to use these to orientate your map. Now, I'm going to get a map out here. I'm going to get a smaller map. We don't need to use a massive one. Here I have a simple orienteering map. Some of you might recognize this from BP Sunday. And on this map, there are some lines and some arrows. On this, these are pointing to magnetic north. Very important that you check whether your map is pointing to magnetic or true north. We'll touch on that a bit later. But for now, let's work with the fact that we are pointing our map towards magnetic north. Our compass points towards magnetic north. Now, if we know where we are, it's always a useful thing to have with a map. What we do is we take our compass, we line up its edge with our north arrow lines, right? Making sure that the top of our compass is pointing in the direction of the arrows. Then, before we go any further, let me backtrack a second here. You'll notice around the edge of this compass, there's a dial that can turn. Right? To start off with, let's just make sure that north on the dial is aligned with the up arrow on our compass. That means that whatever we're going to do, we're going to try and point ourselves towards north. All right. If you look in the middle, let me move the needle out the way. You'll notice that there's a little arrow inside the housing that we can turn around. So I've now lined that arrow up with our main arrow. So everything is aligned in the same direction. We'll get to what happens when we turn it around a bit later. Everything's lined up in the same direction. So we've got north on our map. We've got north on our map, north at the top of our compass, and north on our dial. And all of those things are lined up. The last thing we need to do is make sure that our needle is pointing north as well. At that point, everything will be lined up and we'll know which way north is. The way I usually recommend this is to hold the compass in front of yourself, right? So you're looking straight over the compass. Remember, your map is lined up with you as well. Just put it down to keep out of the way. What you then want to do is often people will then want to turn the compass until the arrows line up, or turn the dial until they line up. And that's not achieving much. What you want to try and do is turn yourself. So I'm going to be holding my map, holding my compass, and I'm going to turn my entire body until everything is lined up. Once that's done, I know that my map is facing north, my compass is facing north, and I'm facing north. From there we can do a whole bunch of other things, which I'll touch on a bit later. But that is broadly what one of these compasses is intended for. We'll do a bit of other stuff later with measuring angles and bearings. While I'm at it, I'll just show you. This is another kind of base plate compass. Let me just see here. My stream seems to still be fine. Sorry, I see there was a message about somebody losing connection. I'm just going to give ourselves a moment to make sure that everything's still working. Everything seems to be going fine on my side. Yeah. Right, I'm going to carry on then. So this is another kind of base plate compass. It's a bit of a simpler one. It's an orienteering specific compass. And the nice one about this is that I can strap it to my thumb so that I don't drop it whilst running around in a forest. And I can still see through it, and I can use it to point to myself on my map. But ultimately, its purpose is exactly the same. It's a base plate compass. The next kind of compass that I'm going to show you is what's called a lensatic compass. You get a number of different types of compass like this, lensatics or prismatics, and they look like this sort of thing that just popped up on the screen. These are your sort of quintessential adventure movie compass, and we've got one here. Obviously starts off folded away, and this one's a little bit tricky to actually show you what's going on because the sighting piece doesn't open up all the way. But what you'll notice in the background there is there's an entire card that's magnetized. Let me bring this in here and hopefully you can see it spinning. And because I'm holding it at an angle, it's not going to spin very nicely. Same reason as I mentioned earlier, because of the magnetic inclination. I'll just put this on a really steep incline. But at the background there's an entire card rather than just a needle. And the card has all the compass bearings noted on it. Right. The purpose of one of these compasses is not necessarily as much to set a map. You can use it to do that. The purpose of one of these is to make it is to help you when you're taking bearings. And we'll touch on what a bearing is in a bit. But the idea is that if I hold it like that, well, let me show you some of the features first of all. You'll notice there is a slit in the back cover here, and in this little plastic jobby here, there are a couple of things. First of all, there's a little lens here, a little magnifying glass type thing, and it'll be really hard to see, but there's a very thin slit just here. If I hold it to the camera just to the right angle, you can see the light shining through it. Alright, so that slit is going to be very useful for us. So how does this work? Well, you open it up like so, in this particular case. Some of them you'll actually stand the ends upright, but however it works, the idea is that you can look through that thin little plastic slit up there and our big background slit at the same time. And I'm going to hold it to my eye like so, and that should enable you to get a very precise angle on a very thin field of view. So if I'm looking far off into the distance, I want to make sure that I'm getting the bearing slightly at the trig beacon, not sort of at the trig beacon. I'm going to line myself up and look through and spot that. Now, what's nice is that our little lens here acts as a magnifying glass and it's slightly angled. So by just flicking my eye, I don't need to move my head, don't need to move myself, don't need to move anything else. Make sure I'm still looking exactly the same direction. I can look through there to see what's going on our dial below. So if I do that, rather pointlessly, I'm going to take bearing of my webcam, and presently this is sitting on about 247 degrees. So that is what a prismatic compass is. Well, lensatic in this case, it's got a lens. The prismatic ones have a small prism that enable you to do the same thing. See what's far in the distance and what's going on the compass at the same time. When these compasses are sold, they usually are quite accurate. They're usually specified as having a particular accuracy in terms of what level of sort of sub-portions of degrees they can actually measure. I don't know what this one's specificity is, but usually they can you can use them to get very, very, very precise bearings, half a degree or a quarter of a degree even. So that is our prismatic compass, or lensatic rather, in this case. Sorry, I keep getting the two confused. Right, so that is our different types of compasses. Right, we've explained some stuff about true north and magnetic north earlier. If any of you are looking at your badge requirements, there's also something called grid north. I'm going to touch on that in the later session when we deal with maps and how they are working. So, as I mentioned earlier, we're going to want to work with true north and magnetic north. And it's very important to know what you're actually working with. For most practical purposes, if you're taking bearings and you're going to be using those in the short term, you will probably stick to magnetic north. I'll explain why you might want to use true north a bit later. Right, so what ultimately is a bearing? So a bearing is a measurement of direction. So we always said we can align ourselves to north, and obviously if I turn around and face the other direction, I'll be facing south. But we can get ourselves east and west. But what's going to be quite useful a lot of the time is to get really precise somewhere between north and west. And how are we going to actually specify exactly how specific that angle is? And that's what a bearing is. A bearing is how we're going to measure that. If you've used your mathematics set in school, we've got a protractor, and a protractor is a tool used for measuring angles, and ultimately that's what a compass is. You're just measuring that angle on the earth. So how are we going to do that? So we're going to use our base plate compass again, because that's what most of us have got and how we can use it, what we can use. So the first things first, if I say that we're going to be heading on a bearing, and for now let's say that that is a magnetic bearing of 60 degrees. How are we going to go about doing that? Well, best way to do it is to use our dial here and turn it so that the number 60 is what's aligned with our arrow. That says we want to go in the direction of 60. Once again, we're then going to do our same trick. We're going to turn ourselves. And what we're going to do is we're turning ourselves until such time as our arrow isn't pointing at the top of the compass anymore, but is pointing into the little arrows at the background. Right. That means our arrow is pointing north and we are pointing in the direction of 60 degrees. Right. That's how you take a degree and you effectively input it into your compass and make sure that you go in the right direction. Once again, I can't stress enough, the best plan is you always to turn yourself. As soon as you start turning the compass, it's like, oh, we must go that way. Well, actually, much easier if you turn yourself and say, I'm now looking in the direction I need to go. How do we do that in reverse? Right. So what we might want to do is say, well, what bearing are we going on? Right. This is very useful if you're keeping a log of a hike. Say, well, what direction did we hike in? That might enable other people to follow along and to repeat your steps later. So how do we do that? Well, what we can do is we're going to face the direction we're going, keep our compass pointed that way, and this time all we do is we turn the dial until such time as the norths line up. So in this case I'm going to turn it until such time as norths line up. Alright, wobble it around, and then what we can do is we can read off the number that is at the top of the dial. And that says we're currently heading on a bearing of, in this case, 290 something. Right. With a base plate compass, typically you're not going to be able to get that accurate number. Probably the best you can do is to the degree. If we're using one of these to take a bearing, same idea, you point yourself at the object. In this case you wouldn't need to turn anything to line it up because the entire disc is spinning. You'd just be able to look through the slits and look down through your lens to read it off. And that is how you take a bearing. Now, the important thing to remember is that those bearings are in magnetic north. Give me a second, just got some messages. let's check here. I'm trying to see how far behind live my stream is at the moment. Sorry, just got a few questions coming in here. Right, let's carry on then. So we've said that that's how we can use one of these guys to take a measurement of direction, and yeah, so just checking some questions coming in here. Bearing is a measurement of direction. So we are saying that we're going to be going in a particular direction, i.e. on a bearing of 240 degrees. That tells us what direction we're going in. The degrees themselves are, as in a circle, which you'll touch in school, a 360 degrees in a circle, and you'll notice that lines up with what you've got here on your compass. And effectively what you're saying is, on what part of the circle am I heading? If north is at the top, I want to head that way. And that is a particular bearing. Anyway, back to magnetic and true. So magnetic north is what your compass is going to be giving you, and if I'm taking some measurements now and giving them to someone who's going to be using them in a very short space of time, that's probably sufficient. You can get away with using magnetic most of the time. But it's the problem is, as I mentioned earlier, if we remember our balloon Earth, magnetic north shifts over time. So what was magnetic north when you took the bearings, or when the map was made, isn't necessarily what magnetic north is today. So if I tell you to go on a bearing of 137 degrees, but I don't specify when those measurements were taken, those might not be what they are today. Let's have a look at an example here. We'll touch a bit more on maps later, but you'll notice on a number of maps, just hold one up here, you can see, this is a 1 to 50,000 map, and you can see on the side there it's telling us what our magnetic declination is. I apologize, I don't know if I held that up straight for you at all, but I'll just read it out here. And this one says to us that our magnetic declination is 19 degrees, and it's 0.2. And it's got a mean annual change, sorry, that's 19.2 degrees west, and it's moving eastwards by 2 minutes. Maybe that's an important thing to talk about. Weirdly enough, the sub part of a degree is something called a minute, and a subpart of that is a second. I'm not 100% sure on the history of why, but degrees are broken into 60 minutes, and minutes are broken into 60 seconds. It does mean that it's sometimes a little bit awkward, especially if people give the measurements in decimal versions of that. I'm not going to delve too deep into using that. The important thing I wanted to take from that is that that one says that it's moving slightly eastward every year. Now, thankfully, this map also tells us that these measurements were taken in 1980. So they're probably a little bit outdated by now. And if we were to keep up that same shift that they told us about then, it might have changed direction, it might have accelerated, we don't know. So what I'm going to do is I'm going to quickly flip back to my display, and I'm going to zoom in on the Drakensberg, where that map is of, and check what the declination is today. So today, that declination is -23 degrees. So although our map here started off with a -19 and actually said it was shifting eastwards, since this map's been made almost 40 years ago now, it's actually moved further west again. So, and in fact, it's moved by about 4 degrees. So if I told you to go on a particular bearing and you were just using the information on that map, you would actually be heading 4 degrees off. Now, 4 degrees doesn't sound like a lot, but and maybe I'll do the maths in the break and explain it to you nicely in the second video. But that 4 degrees can add up to quite a difference over a particular distance. If you're just measuring something around, say, Delta Park or around your scout hall, you might find that those bearing differences don't add up to that much, and it's not that important. But over really long distances, it can definitely add up. So that's why it might be important to give magnetic or true bearings. So if I give magnetic bearings and I don't tell you when they were taken or what the declination when they were taken is, you might not know how to be able to use those in practice. So that's why what we'll often do is convert our bearings into true bearings. And this will mean that later on it's easier for someone to reverse engineer the process and take those true bearings and apply the magnetic declination that they're encountering now. And basically this just boils down to maths. Alright, you're going to take your compass and it's going to say, and you figure out that there is a bearing of 60 degrees, and your magnetic declination is, let's be nice to ourselves and just say that it's 20 degrees, and 20 degrees, with 20 degrees, you would then need to say, right, well, is it negative or positive? And what we usually specify is that declination westwards is negative. So if we say that the magnetic declination is westward, what we're saying is that we need to minus off 20 degrees from whatever's on here. So I've measured that it is magnetic 60. What that means is that in true bearings, it's actually only 40 degrees. And then we will do the reverse the other way around, and we'll say, well, hang on, this is a true hang on, I'll put that the right way around. Do give me a second, I don't want to tell you the wrong thing. Give me a moment here. I don't want to tell you the wrong thing at all. Apologies, I'm doing that the wrong way around. So, if we say that magnetic declination is 20 degrees and it's negative, that is what we apply to true to get magnetic. So if we're going from magnetic to true norm, we want to do that in reverse. So if we take a magnetic bearing of 60 degrees, that means that the true bearing is actually 80 degrees. And if we get a true bearing of 80 degrees, we'll then minus our 20 to get our 60 degrees. I hope I've got that right this time around. Otherwise, there'll be a errors and corrections video coming up later. But I will double check that all. Right. And yeah, that's all that magnetic declination really comes down to, is just making sure that you add or subtract the right thing, which I'm not 100% certain I've done now. I do apologize for that. All right. Right, that is how we use these. The next thing that you can do. Let me just get some extra stuff set up here quickly to show you. And downloads, where are we? Hang on. Do apologize. Let's pop one of these in. And alright, let's bring that. Yeah. So what we have here, pop one up on the screen. And I'm sure if you've been out hiking, you will have seen these. These are what are called trig beacons. These are actually used by land surveyors to pinpoint locations, and when we touch on maps a bit later, you'll actually see how they're noted on the map. But the idea of these is that you can use these to sight to, and take your compass out, look towards the trig beacon, and find yourself and find a bearing from it. And then what you can do is you can use that to try and locate yourself on a map. So I'm going to flip over to my screen capture here. And let's find that. And let's go to display. Right, I do apologize for this being a little bit low budget, but this is just a blank PowerPoint slide that I'm going to do some drawing on. Now, what you're going to do is let's pretend that there are some things that we can see. Right. Let us check here. I tell you what. Let me pause the stream for about 10 minutes, just so I can set up some slides here quickly, and when we come back, we can deal with the bearings and how to use them to locate yourself or locate objects. All right. Let me put this back on. I'll be seeing you in about 10 minutes. We'll send a message out in the WhatsApp group when we're about to start again. Hey everyone, welcome back. Hope everyone had a good stretch of the legs and a bit of a break there, and hopefully we're all back for the next round. A couple of questions came in during the break, so I'm going to try and jump back and answer a few of those, specifically to do with the magnetic declination, which I admit I'd bungled slightly in my first presentation of it. So I think the best thing to do is to bring back our little makeshift Earth we had here. And in this particular case here, let me get rid of our trig beacon for now. What we noticed here, well, before I do that, if you look at our compass, all right, our bearings obviously run clockwise 0 through to 360. I did do that I did that the wrong direction. They run 0 through to 360 on our dial. So when we talk about adding degrees, it means we're going clockwise around the dial, and if we talk about minusing degrees, we're going anti-clockwise around the dial. All right. So if we look at our friend here, and we're sitting on magnetic north, in order to get to true north, we need to tick around clockwise. So to get from magnetic to true, in this case, we need to add our declination. This is also a case, this is the particular case, it's a case where, if you think about it, magnetic north is, well, from true north you're heading west to get magnetic north. Apologies if there's some noises in the background. I believe my cat is trying to play with a cardboard box. She did try to come and punch buttons on the live stream during the break. So yeah, our Earth back. So because magnetic north here is to the west of true north, in order to get from magnetic to true, we need to add back our 20 degrees. So this will be a case of where we're talking about having a westward declination, and we need to add back. I hope that makes sense. Richard has sent a good link on the group, which will hopefully give you guys something a bit easier to read through if my explanations have not made any sense at all, which I do apologize about. Right, so let's move on. For the rest of this, I'm going to just be working with the assumption that all bearings we're dealing with are magnetic, and I'll assume that if we've had to convert things, then we've already done so. Let us see here. Okay, cool. So let me move my display back over here. Cool. So here we have our friend, and we're a bit sad because we are currently lost. We know, broadly speaking, where we are on the map. We're somewhere here, because we managed to look around and we can see 3 objects that we know what they are. That is to say, I've looked over here and I've seen that that is the peak of the mountain, and perhaps there is a trig beacon on top of it, so I'm pretty certain I know what it is. And I look this way and I'm looking towards a small dam, and I look this way and I can see a particular road junction or something. We'll deal a bit more with maps later, but for now let's just say that there are these 3 objects that we are able to see. And we've picked up our map and we've looked at the map and we've found these 3 objects on the map. So all we know at this stage is we're somewhere in between them, but we don't know exactly where. And let's actually think about this. Let's understand why that might be relevant. Is those three objects that we've found might be particularly far away, and weirdly enough, we're trying to find this object that is somewhere near us, but we don't know. Are we here and we must walk this direction, or are we here and we must walk this direction? We don't know. All right. So we want to be able to find exactly where we are and pinpoint ourselves so we know which direction to go in. All right. So how are we going to do this? Well, we're going to take our compass over here, and we're going to be standing with our compass, and we're going to take a bearing towards object A. All right. And we obviously take out our compass, and we measure our bearings, and give me a second here. And we measure that object A is on some kind of bearing of, let's say, 320 degrees. So let me just pop that into, not that button. So from here, I measure 320 degrees. And that is towards object A. So then what I do is I pick up my map and I find object A on the map. What I'm going to do, this is why having a base plate compass is really nice, because you can see through it. What we're going to do is we're going to put our compass at object A on the map. Now, very importantly, let's see, we've got an explanation. Please explain how to take a bearing on a lensatic compass. I did cover taking bearings on lensatic compasses. I will quickly recap that now. If anybody's interested, let's pop myself back on the screen. Right. So on the lensatic compass, remember you've got the whole dial that's going to turn in the background there. So what you need to do is get it into its operating position, which will usually be something like that. Right. What you're able to do is, there's a thin little slit over here. Right. See, there's some light shining through that. What you want to do is look through that slit and the slit at the back at the same time. You have to bring it right close to your face to do so. Alright. If you do so, use that and you sight the object that you're looking for. Right? If you're using your base plate, you simply point yourself and the entire compass at the object you're looking for. In both cases, you and the compass are pointing at the object you want to look at. Right? With the lensatic, you're then able to look through your little lens over here, and that should magnify the numbers that are at the back here. All right. You can use that to read off the measurement you're looking for. Some lensatic compasses have magnetic declinations already programmed into them for wherever they're particularly. You'll see different lines on it for wherever they're designed to be used. Some of them, this little brass housing around here, it's quite hard to move, but you can actually adjust it to pre-program in your magnetic declination. Just check if you've got one of these lying around that is or isn't done before you start using it. All right. I did cover that in a bit more detail earlier on as well. Back to our bearings. Cool. So we've measured from ourselves. Remember, we had our compass at ourselves, and we measured our bearing of 320 degrees to object A. What we're now going to do is we're going to take our compass and we're going to place it on object A on the map. If you're using a lensatic compass, it's quite useful to have a separate protractor with you. It's quite hard to get bearings off the lensatic onto a map on its own. What we now need to do is we need to effectively measure backwards from object A to ourselves. And this is what's called using a back bearing. Right? The bearing is what is the direction from me to the object. The back bearing is simply what is the direction from the object to me. Now, as we mentioned earlier, there are 360 degrees in a circle. So whatever our bearing is, all we need to know is what's on the opposite side of the circle. We can either just look at our compass and figure that out, but mathematically, all that says is we need to either add or subtract 180 degrees. So our friend here was 320. If we pop our back bearing in, sorry, give me a second there. Right, so what that means is that we've got a back bearing of 140 degrees, right? 320 minus 180 is 140, all right? So we now need to take a back bearing from object A on our map of 140 degrees. I'm going to quickly switch back to live here. So how would we do that? Well, what we would do, make sure that our map is orientated to north. First, right, we can use our compass, lining up our arrows, make sure the map is pointing north. We're then going to measure, turn our dial to 140 degrees. And we're going to turn our compass, right? We'll leave the map as it is, and leave ourselves as we are. We're just going to turn the compass until it lines up, right? So until our arrow is pointing north again. We'll then know that our compass is now pointing along our back bearing of 140 degrees. We can then use the edge of the compass to draw a nice straight line through point A, pointing on 140 degrees. So let's do that. And what we're going to do is we're going to find a line, and we're going to draw a line on roughly 140 degrees. That's somewhere over here. What we now know is that we are somewhere along this line. We don't know exactly where just yet. Right? We could be here, or we could be here. But we know we're somewhere along this line on our map. All right. So we're a little bit less frowny faced. All right. Now, the next thing to do is to repeat this process with object B. So we take our compass and we look towards object B, and we take a new measurement. All right. And let's say that we measure 80 degrees. All right. What's going to be our back bearing for 80 degrees? It is going to be 260. Confirming that for myself. My brain might not be doing all that much maths. So we're going to say we've got a back bearing of 260 degrees. So we repeat the process. We place our compass on our map. We turn our dial to 260. And we draw our line. remember, I'm presupposing here that we can see what A, B, and C are, and we know where they are on our map. So we go to our friend here, and now we need to measure 260 degrees. And we measure our line, and 260 degrees comes out somewhere over here. Now, what we now know is that A, we're somewhere along this line, and we're somewhere along this line. Well, that must mean we're where they intersect, surely. Hooray! Now, this is probably good enough, right? We now know, all right, we're somewhat south of this object B. We can now measure on our map what the bearing is that we need to follow, and we can and follow it. But it's always worthwhile doing these measurements with a third point. Right. This is why it's called trig beacons and trig survey, because we're going to try and make triangles. Right. We're going to use trigonometry when they do the full land surveying to do these things, but we're just going to worry for now about making triangles. So we have a look and we measure to object C, and we see that object C is on a bearing of 220. So we know then that our back bearing is going to be 40 degrees. So let us put that in. Back bearing 40 degrees. And we draw a line with that. So let me find my shapes. And so we then are able to say, all right, 40 degrees is like so. Right, let's put our compass there. Now, if you're very lucky and you've done this perfectly, these three lines are going to intersect in pretty much exactly the same spot. And you're going to be very confident you know where you are. But in reality, one or more of your measurements might be slightly off, or you're sighting towards a particularly large object, so you might not have lined up the same point that you're looking at with the point on the map, and you wind up with a relatively largish triangle. It's called your triangle of uncertainty. And all of a sudden, you're not quite as happy as you were. Now, hopefully, that small area is small enough for you to still get a good idea of where you are and what you need to know. And perhaps you can use that with some other information to that's actually on the map to orientate yourself nicely. But it's always worthwhile doing the third one, because what you might find out is that you were really off. Is that you wind up with these intersection points being very far off. And then that'll tell you that, okay, maybe one of these measurements that I took I didn't do correctly. And then you can go back and confirm. And you see, hang on, actually, this guy, I hadn't done him totally correctly. You remeasure and you find out that this is the correct point. All right. It's always very useful to have a third measurement. Now, while we're on the topic of back bearings, maybe something just to bear in mind is this is how you use a back bearing. So it's always important that if you write down a back bearing, you specify what the back bearing is from. Often I see it in high clogs, and we'll touch high clogs but in this afternoon session, where people say, we're on a bearing of this, and therefore our back bearing is that. The back bearing is only useful if you say what it's to. So we might be walking on this particular bearing, but there is an object that is in another direction. And that is what we've got a back bearing from. So don't just throw back bearings out willy-nilly. Always make sure that your back bearings have a point. here, in what we just showed, they were being used to help us locate ourselves by using different back bearings together. Another way of using back bearings is maybe you're at a particular object, and maybe it's a very, very prominent object. The peak of a hill, or a really tall tree, or a radio tower, something you might encounter while you're out there, something that you know you'll be able to see again in future. We're going to walk away from our object on a particular bearing, say 90 degrees. Now we're going to walk, and maybe we end up doing a little bit of this to get over or around objects. And we want to know, are we still walking on the same line that we started off walking? Well, we can turn around and face the object that we need to face, and make sure that that object is still on that back bearing. So we started walking on a bearing of 90. The object that we're walking away from should remain on a bearing of 270. That's another way to use back bearings. Right, let me have a look here. What do we want to cover next? Right, so the other way that we're going to be using our bearings is to locate objects. So let me put my display back on. Right, so there are three very similar objects, right, over here, and we want to know which one of them is which. Right, we've got our map, and we know where we are on the map. And on our map, say these are three objects we can see on our map. And we know where we are on our map, right? We've just managed to do that using our method beforehand. Right, let's just put ourselves back there and make a smiley again. All right, so we know where we are on our map. And on the map, there are three objects that we can see that are similar. They might be, say there's three buildings noted on the map. And we're looking out, and we can see one building. Now, are we seeing this building? Are we seeing this building? Or are we seeing this building? We don't know. Right. So what we can do is take our compass and sight the object that we're looking for. Right. So we take out our compass and we look through it, and we decide that, or we measure rather, that the object we can see is on a bearing of 45 degrees. Right. Well, is that building that I can see, is that this building, or this building? Well, on my map, I can place my compass, and I can draw a line. Whoa. And I can draw a line on an angle of 45 degrees. Now, obviously allowing for a little bit of error there. We can see that, hang on, that 45 degree line, that's pointing pretty much towards object B. Right. So that tells me that the building that's in front of me, the one that I can see, is indeed object B. To be certain, what we might do is we might take ourselves and move ourselves. Well, let's move ourselves to another point that we know on the map. And repeat the same trick. So if I've started here and I've taken a bearing, what I can do is I can walk further down the road perhaps, to another point that I know on the map and take another bearing to our object. And if I do that properly, and I take a bearing, and this time I see that it's on a bearing of 355, and I see, hang on, that one also points at building B, then I can be pretty certain that the building that I am seeing is in fact building B. Right. That is how to identify features on a map and take bearings to locate them. That's how to locate objects and determine which objects are which. The other way to do this would have been back when we were at the start. Is to measure on the map the angle or the bearings to each object. So we measure one up here, and we measure one out here. And we say, well, if we're doing this correctly, then object A should be on a bearing of about 0 degrees, B on about 45, and C on about 60. And if we know that that's what A, B, and C are on, we can then say to ourselves, well, if the one that I can see is on a bearing of 45, it must be B. I hope that makes some sense. All right. Cool. I think that covers everything that we were going to go through on compasses and bearings. I'm not sure if there's anything else we need to go through on bearings. So what I'm going to do now is awkwardly sit around for a bit and let some questions come in on the WhatsApp group. So if you do have questions, stuff that I haven't perhaps covered in depth enough that you'd like me to go over again, please send those questions in now. I'm going to have a check and see if there are any questions I haven't already got to. So yeah, fire away with questions. I see there's a question that came in a little while ago. Let me see if I can pull up the image on the on our screen for us, and we can share what that's talking about. So give me a moment here. Ooh, that opened quite big. Right, so we had a question about one of these compasses and how to use it. This is effectively just a base plate compass, very similar to these guys. In fact, probably its closest cousin in some senses is this one. This one has no turny dials, like this one. So you have to be a little bit more creative in how you use it to ensure that you get your bearings. You don't have the swivel housing to work with. The important thing there, let me bring it back up again, to note is that you're always going to want to keep the same concepts of point yourself, north, and the compass and the map all in the same direction. So if you can do those four things, then you will be able to work with it. A bit harder to read off bearings. The important idea there would be make sure that north is pointing the correct direction. I don't know if that one... No, that one doesn't swivel. Right, so if your... whatever direction your arrow will always be pointing north. The number underneath it will be the direction that the little... let me see if I can... The top end, the slightly pointy end of the actual compass housing is pointing. So if your arrow is hovering over 60, then that is the direction that the top of the compass housing is pointing. All right. Let me have right, so I've got some questions coming in here about back bearings again. Right, so let me just recap back bearings. All right, so the bearing is the direction from yourself to an object. Right, back bearing basically implies that what you're looking for is the direction from the object to yourself. So if somebody else was standing at the object and they had a compass and they were looking towards you, what bearing would they get? All right. Why is that useful and how do you use it? All right. So remember that I've stood there and I'm taking my compass out and I've looked towards an object. By doing that, I've taken a particular bearing, right? But so let's say that I've done that and I've swiveled my dials and I've picked up a bearing of 140 degrees, right? So if I want to use that back bearing, let's say it's a back bearing to check that I'm still walking on the same in the same direction. So I'm walking on a bearing of 140 degrees. But I know that I left behind my piggy bank over there, and the piggy bank is going to be on a back bearing of 320 degrees. So if I want to check that I'm still walking in the same direction, actually let me pop up a slide here so you can see why this can go wrong. And let me throw some shapes up here. Give me a second. I see there's some more questions coming in, so we'll get to them shortly. Give me a moment here while I set this up for us. Be with everyone very shortly. I do apologise for awkward time it's taking here. And Right. Right, let me pop my screen sharing on here. I think there's actually going to answer a couple of questions that have come in. Right, so we're over here at the start, and we can see the end is over here, and we know that we need to walk on a bearing of 90 degrees to get there. All right. Now, we start walking along our bearing of 90 degrees, but we come across a river. All right. And, out in the line hunt, we can't go over it. But there's a bridge somewhere down the river here. So we now head up here, and we cross the river at the bridge. Now, from over here, we can't see the end. We can't see exactly where we need to get to. So how do we get there? Well, what we might want to do is just carry on walking on our bearing of 90 degrees, because we know that's what we needed to do. The problem is, we're no longer on that line. We're somewhere up here. And if we carry on walking on this, we're going to wind up at this point. Now, I don't know what this is. Let's pretend this is something dangerous, where we don't want to be. So just following our 90 degrees isn't very useful anymore. So what we do in this instance is we're going to take a sighting back to our start. And what we're going to do, we're going to say, well, we know when we started, if we were walking on a bearing of 90, our back bearing was 270. Right? 90 plus 180. So we want our back bearing to be 270. Presently it's not. Presently it's only about 220. So what we're going to do is we're going to walk down the edge of the river here. Walk down the edge of the river, until such time as our object is on a bearing of 270. And that'll mean that we're back in line with where we needed to be. Which means that now, if we turn around and we walk on our bearing of 90, we're going to be back to where we needed to be. So that is how you can use a back bearing to do what you need to do. Right. I hope that makes some sense. Some questions here. If you lose your bearings, what are some best improvised markers to use? I think we'll cover some of that when we get to the next video where we deal with maps specifically. Let me put myself back on display. We can discuss that when we get to the maps video at 2 o'clock. I think that there'll be a lot more things will make a lot more sense when I explain it on that. All right. Which is better if you don't have a map, lensatic or baseplate compass? I wouldn't say there's a better one. Ultimately, compass is any type of compass is kind of not that useful without a map to use it, because you kind of need to know what you're navigating towards. All a compass does is give you in which direction the North Pole is. Unless you've got a team of reindeer, that's not really going to be that useful to find your way home. So ultimately it comes down to what you're using the compass for. I personally prefer my baseplate compasses because they're quite easy to use in conjunction with your map. That said, you invariably lose a little bit of accuracy in your bearings and sightings. That's why it's important to remember the triangle of uncertainty that we mentioned earlier. Your lensatics are going to be much better for getting accurate readings and accurate bearings, but it's harder to then translate those bearings back onto your map. Unless you're also dragging along a protractor so that you can do those measurements on the map. Cool. I covered this right at the top of the video, I think. If I didn't, apologies for that. But how are we actually going to test all of this? So obviously these videos and these questions and answers are awesome for you guys to be able to learn. Unfortunately, a lot of the practical stuff you need to do to actually go out there and take bearings in an open space, we can't do at the moment, seeing as we're on lockdown. We will send out some Google surveys for you guys, some little multiple choice questions, and some written theory questions for you guys to answer, to test some of the theoretical aspects. But realistically, some of the more practical things you are welcome to attempt to practice in your garden. But you will probably only be able to put them properly into practice when the lockdown is over. We'll probably try and organise maybe a weekend or just a day, seeing we don't need to go through all the theory when lockdown's over, to meet maybe at the Greenside Scout Hall or some other location, and we can put this all into practice. Yeah, I hope that's all good. I'm going to give us a few more minutes to catch the last few questions, but we shall see what happens. Let's see. I think there's some questions. Right, getting back to stuff. Yeah, I hope I've answered all those questions. And if there are more questions, feel free to keep dropping them on the WhatsApp group. I myself, also, if you're Richard, will do our best to answer them. And I'll see everybody back at 2 o'clock for the maps section of the Scoutcraft badge.